Hello. So in this video, we'll be looking at the graphs of sine, cosine, and tangent, which obviously we shorten that to sine, cos, tan. Right. So I'll be looking at these three graphs. Now this is basically GCSE. But I want to go over some particular topic questions that will be important later on in the course. Um, And so, as I said, for the rest of this topic and the next topic, we'll be really delving deep into sine, cosine, and tan. As a foundation, it's best to consider what their graphs look like and the values they sort of take. That's what we'll be looking at in this section. So the graphs, which should be just a recap from GCSE. But yeah, so let's dive into it then. So firstly, we have sine. So we say sine of x, right, or sine theta, or whatever we have. So we have an angle x, and so we do the sine of that. And so if we plot the graph, then y sine of x, the values of sine of x are right. So firstly, let's start from 0 here, with x is 0. And so the graph starts at 0 as well, right? And so then it has this sort of shape here. After 0. So then some notable values then. It has this sort of like hump sort of shape. So at 90 is the top of it, when it's 90 degrees. So that's when it attains 1 there. Then it goes back to 0 at 180 degrees. Then it shoots down here to -1 at 270 degrees. And then lastly, it goes back at 360 over here. And so those are the key sort of values, of the graph. So it starts at 0, when x is 0. Then it shoots up here to 1 at 90. Then it goes back down here to 0 at 180. Then it drops down to -1 at 270, and then it goes back at 360. And actually, the graph repeats itself after that. So if we were then to extend this, it would repeat the same sort of shape, right? Let me draw that again. There we are. Okay, roughly the same sort of curve, right? So then that's 360 there. So then it goes back to 1 here, 90 degrees after. So that'd be 450 degrees. Then obviously the next after another 90, it goes back to 0 here. So that'd be 540. Then it goes to -1 here at another 90. So that'd be 630. And then at the end it goes back to 0 at 720, and it will continue repeating in this way, right, forever and ever. And what we call that then, this sort of graph that repeats itself forever and ever in this way, we call it a periodic graph. And so then that and then we call the period the values of x when it starts to repeat itself. So as we see here, it starts here at 0. Then at 360, it then starts to repeat its shape again, right? So then 360 is the period there, right? So that's saying every 360 degrees, the graph goes back to its side, essentially, right? And so what we could say there then is, for any angle x, sine of x, then sine of x plus 360 would get me the same result. And actually then, if we add another 360 on, that's the same as x plus 720. And so that's the same as x plus then, add another 360. So 1080. And so it goes on and on and on, right? So every 360 degrees, the graph repeats itself and goes back to what it was, right? Okay, and also you can go backwards as well. So if I get rid of this then, this idea of the period, for a second, the graph goes back, and we can go backwards as well. So then if we where should I? There we are. Okay. So if we go back by three, if we go backwards instead, to -1 there. So we start from 0, and then when it goes down here to -1, that's going to be 90 degrees. So it's going to be -90. And then it shoots back up here at 180. So that'd be -180 because it's on the negative x-axis. And then it shoots back up here to 1 at -270. And then obviously it would go back down there at -360, right? And so and then obviously it repeats the same sort of shape, right, backwards. So it's the period of 360. So yeah, so that is essentially the sine graph. Hopefully you can see the values. I'm sorry, the position, the axis, where I put the numbers isn't the clearest, but that's the whole idea, right? So very simply then, the sine graph between 0 and 360 looks like that, right? So 90 there, 180 here, 270 there, and 360 there. And obviously we have an x-axis, and this is the y-axis. And so from this basic graph, right, we can then continue the graph forever and ever, right? Because obviously, again, it repeats itself after 360 degrees, okay? The other thing to note is then it'll have a maximum and a minimum value. So the highest point the graph reaches, which should be up here, and the minimum point where the graph reaches down there. And so the max value is going to be 1, and the minimum value would be -1, okay? So those are basically the key ideas and the things you need to know about the graph, right? So you should remember the basic graph between 0 and 360, and then the idea it repeats itself after 360 degrees, right? Backwards and forwards, to the left or to the right, because the idea that the period is 360, so after 360 degrees, the graph then repeats itself again, okay? Right, okay, as that's sine. Okay, I'll box that then. There we are. Okay, now the next one's cosine, right? So again, with cosine of x cos x, then we can do the same thing. Start to plot that graph. And so then, for the first 360 degrees in this case, it doesn't start at 0 like sine. It doesn't do that. It starts from 1. And so it comes down in this case. And so it has that sort of shape instead. So you can also remember the graphs like the shapes they look like. So the sine graph looks like an S, right? The cosine looks like a C. So obviously it starts with a C, the sine starts with an S. So that helps you remember the graph that way, or the shape the graph looks like. That might help. But the cosine graph looks like this. So the key idea that it starts at 1, not at 0, right? But the behaviour is pretty much similar, right, to the sine graph. So it starts at 0 here, and then 90 is when it goes back to 0, then 180 is when it dips to -1 down here, and then 270 is there, and then it returns back to itself at 360. And then the graph again sort of repeats itself. So again, if I was to then do the next 90 degrees, that here would be 450. it dips at 540 after, another 90 degrees. Then another 90 from 540 to 630. And then it goes back up at 720. Right, so then it repeats itself again after that, right, if we were to continue the graph after that. So again, it has the same sort of periodicity, right? The same period, the idea that the graph repeats itself every 360 degrees. Then we've got, it starts at 0 here, then 360, so then it starts to drop back down again from the top, and then 720, it returns back to that same position, and then it continues the same shape of the cosine graph, right? And so again, the idea is, again, the period is going to be 360 degrees, meaning, again, it repeats itself every 360. We can also say that cosine of x is then the same as the cosine of the same angle add 360, or you could take away 360 as well. Because of the fact that the graph repeats itself, it's the same every 360. Okay, so we can express it like this, and then also the idea, again, the maximum, the highest point it reaches is going to be 1 up here. And again, the minimum is also -1. So there's a very, very, very similar to the sine graph. Probably the only key difference is that it starts at 1, not at 0, unlike the sine graph. Okay? And again, because of this period, we can go backwards as well with the graph like that. Let me draw that again. There we are. Okay, a lot better. So then we could go backwards and say, well, if we start at 0 here, then it reaches 0 at -90. Then another 90 backwards, it should be -180. It goes down to here. Then 270, it goes back to 0. And then 360 when it reaches here. And then it -360. Then again, it repeats back to where it came from. It goes back to its starting position, if you will. And then it continues to graph backwards in this way. Okay. So that's the idea then, alright? So again, then we really only need to consider like the first 360 degrees, because then after 360 degrees, it again repeats the same shape. So then we have cos x here. And so then if we draw it from 0 to 360, we have that. Then that would be 90 here, it'd be 0 here. Obviously it'd be 1 here, then -1 down here. Then 180 is the next one. 270 is the next point, and then 360 here when it returns back to where it started from. So that is the basic cosine graph here. So again, if you needed to then draw any degrees further than 360, obviously then you just continue the graph, the shape of it. Likewise, if you go backwards, you do it in that way. Okay, but that's the basic cos graph then. So again, these key properties, where the period, meaning it repeats itself every 360 degrees, and the top and the max and the minimum value at 1 and -1. But okay. And so lastly is the tan graph. So again, let's consider the first 360. Well, at 0, it starts at 0 again, like the sine graph. However, it's a bit of a different graph to the other two, because what happens is it's sort of like an asymptote. It shoots up like this, right? And so what happens is it tends towards a vertical asymptote, a vertical line like this. So remember, an asymptote, when we looked at the graph of 1 over x, say, it's something that tends to, it's a line that the curve tends to and approaches to, but never actually touches. So it shoots up towards infinity in that way, but never towards the line. And that line is actually at 90, right? So this would have the equation x is 90, okay, the asymptote. And then it shoots back down from negative infinity. So it's very similar to like the reciprocal graph, right? And so then it returns back to 0 at 180, right? And then it shoots back up again, like this. and then again it tends towards an asymptote at 270. And so then it repeats itself again. And so then it goes to 360 here. And so then it would repeat again, right? But I'm just going to leave the graph there. So this very different sort of graph, right, to the other two. The whole idea being it's sort of like a reciprocal, right? It's going from like negative infinity, coming upward like this, and it's going towards this asymptote here. So basically, it's between two asymptotes, right? The curve, right? As you can see, yeah, and the asymptote every 90 degree, every 180, but the first one's at 90. So then the next one is 270 and onwards. So actually, also notice then it starts at 0, and then it next reaches that point 180, and then it repeats the same sort of graph, right? It shoots up at so 0 again. It shoots up like this. Then 180, it's shooting up. It's still shooting upwards. So the graph repeats itself again, right? The shape of the tan graph repeats itself after 180 degrees. If we then continued at 360 over here, it would then shoot up again and repeat the original sort of shape at 0, right? Then there'd be an asymptote down here. Then it would be 270 and another 80, which would be 450, right? But again, I don't need to consider that. Let's just stick to 360. But the idea is hopefully you can spot, right, in a roundabout way, that the period this time is what when x starts to repeat the value, how many degrees when the graph starts to repeat itself is going to be 180 this time, not 360, right? And so yeah, so it's very different sort of graph, the tan graph, to the other two. But also there won't be a minimum or maximum this time. Unless you say the minimum is negative infinity and the max is positive infinity, because obviously it's shooting up to infinity here, and it's coming down from negative infinity down there, right? But obviously that's not a physical number. Infinity is not a number, right, per se. So we say it's unbounded, or there is no maximum minimum, because it just keeps shooting up indefinitely, right? And likewise going downwards infinitely as well. So there's no minimum or maximum, but there are vertical asymptotes. So the asymptotes are where x is 90, and then because the period is 180, it repeats itself again every 180 degrees, then the next asymptote would again be 180 more than this. So 270 then. Then 270 add another 180 be 450. And so then we would continue onwards. And you could also go backwards as well. Right, so if we continue this graph down here, the asymptote there would then be x is minus 90. Then we go from 90 here, and then the next asymptote would be 180 less than that. The 90 take away 180 is minus 90. So you could, so the asymptote, so again the graph goes both ways. And so the asymptote to add or take away 180 degrees from 90, right? So I'm going to say every 180 degrees from 90, right? Because obviously if we have this asymptote at 90, then you add or take away 180, and you get the other asymptotes, essentially, right? Because the idea that the period is 180, so the graph repeats itself in that way. Anyway, so that's the graph then. So again, the sort of core part of the graph between 0 and 180, because again, if the period is 180, it's just repeating itself every 180 degrees after. So there's no so the course, the main part of the graph is the first 180 degrees. So if we do that, the graph will look like this. So it starts at 0, then it shoots up to infinity. And so then it has an asymptote at 90. and then again it sort of goes back, right? Goes back to where it started at 180. There, right? There. Okay, cool. So that's the tan graph then. I'll box that as well. Okay. So those are the three graphs we'll be working with. So hopefully that's just a recap from GCSE, just the way these graphs work. But yeah, as for the tan graph as well, you'll see why there are asymptotes and it looks like a reciprocal graph in the next chapter, because tan is actually a division, right? It's dividing two things, right? Which is like a reciprocal, right? Reciprocal, you're dividing by x. Tan we actually can express with a fraction as well, but I'll talk about that next section. But for now, that's the graph of tan x. Right, so with that in mind then, again, the idea of periods, right, the graph repeats itself every 180 or 360 degrees. There is no cut-off point for the graph goes on forever. So questions you might see the question tell you to only draw for certain range of angles x, right? So this graph here will be between 0 and 180 degrees, right? So you would express it in this sort of interval inequality notation, right? Where you express the values of x you want to draw the graph from to restrict it, right? Because obviously, again, you can't draw the graph forever. But we'll see some questions now. Yeah. Okay. So let's have a look at an example then. We need to sketch the graph y cos theta, which will in this interval. So this is saying between the theta has to be between minus 360 degrees and positive 360 degrees, right? Okay, so if we then draw the graph here, well, again, the first 360 degrees, if we start from 0, so again, hopefully you remember, it starts from 1, cosine. So it looks like that, right? A sort of C shape there. So then if we sort of label the key points, so 90 would be here, 180 would be there, and that's when it's minus 1 down here. Okay. Then 270 would be there, and 360 is there when it goes back to 1. Okay, cool. But then that's between 0 and 360. We want to go back to minus 360. So then we need to draw the graph backwards to 360. So if we draw the graph backwards, okay, there we are, something like that. Let me draw it once more. There we are, something like that. And so if we then we extend our axis. So this is the x. No, this would be theta, wouldn't it? Theta here against y, because it's not x, it's theta here. Anyway, so then the next 90 degrees would be backwards be here. That would then be minus 90 because we're on the negative axis. So then it goes down here at minus 180, and then 270 or negative 270. Then it goes back to 0. And then it shoots up here to 1. At minus 360 there. So that's the graph between minus 360 theta and 360. Okay, so do make sure you understand that that inequality, which tells you the range of values you consider in the angle to be. Right, so that's the graph then. Then part B then says, firstly, sketch the graph y sine x. This was cos theta. So now we need y sine x in this interval between minus 180 and 270. So we're going from, minus 180 degrees all the way to 270. So again, let's draw our axis. So let's do the positive part first, right? Between 0 and 270. So if I copy the interval here, so we need to go to 270, right? So with that in mind, then the sine graph starts at 0, so it's going to be sine here, and then has the sort of same behaviour as the cosine. Now, if I drew it all the way to here, this would be 360, right? This is 270 down here at the minimum value of -1. I only want to go to 270, so what I need to then do is I need to erase, well, not the whole graph. I needed to erase the last part of the graph, and it needs to end there. 270 is sort of the end point, as you can see there, the end of the inequality. So actually, there it is. So then, if we jump to every 90 degrees, then this would be 90, and this would be 180, and then we get to 270. So that's the whole idea with these sort of graphs. The key part is that you just jump in every 90 degrees, right? Any major thing happens every 90 degrees. So, for example, we start here at 0, then it jumps to 1 at 90, then it goes back to 0 at 180, and 270 jumps to -1. So this whole change, we're going from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1, it changes every 90 degrees. So 90 degrees is really like the key sort of values we're looking at, so every 90 degrees, right? Anyway, right, so that's from 0 to 270, but we need to actually go backwards to negative 180. So then we need to extend the graph backwards as well, so it looks like that. Okay, let me draw that again. There we are. But again, I don't need to consider anything further than this, because if we extend the axis, this would be negative 90, because then it will go to -1 down here, and then 180 would be there. So that's it then, right? So we don't need to consider anything further than 180 in this case, because obviously that's the other end of the inequality. So that's the end point there as well. So that's the graph, right? That's the value. That's the angles we're interested in between -180 and 270. Right. Okay. Now part 2 says sine of -30 is not -0.5. Use your graph to determine 2 further values of x, for which sine of x is -0.5. If I jot this down somewhere, but we are told that basically x is -30 is a solution to this, because we were told that sine of -30 equals -0.5. So therefore, -30 for x is a solution to that equation. And so -30 degrees then, if we mark it on a graph, would be somewhere there, right? And so then it's asking to find the other solutions, which is basically then, we did a bit of this already when we looked at the sine rule and the ambiguous case with triangles earlier on in the chapter. But the idea is to spot the other solutions with the same value. Well, then we just read across the graph, right, like this. Straight ahead, either side. Because obviously this represents the line at y is -0.5. Well, that's all the solutions to when the curve equals -0.5, right? Anyway, so we have this sort of line then. So then we try to find them when the other intersections are. So we know this intersection here is 30, -30. But then we've got another one here and another one there, when that line crosses the curve again. So there will be 2 more solutions then. So this is where then we need to pay attention to the symmetry of the curve, right? So firstly, well, if this is, so firstly then, well, again, we have this intersection of -30. What about this one then? What x value or the angle would get me that point there? And then this is where we need to pay attention to the symmetry. Hopefully you spot that the gap again between -180 and at the end of the curve and there, it's the same as the gap between -30 and 0 there, right? And so actually this gap then is going to be 30 degrees, right? Because obviously we're going from 0 to minus 30, so the gap overall is 30, right? So then this gap's going to be 30 as well. So then between minus 180 and then this next intersection point, we need to go 30 along, essentially. But then the other solution then is going to be x is going to be minus 180, add 30, right? To get to this point there. So we need to go 30 along from this end here at minus 180, which should be minus 150. That's that point there then, minus 150. Cool. But then we've got this other intersection there. Okay. So again, the same sort of idea of the gaps then. And so then the gap between this minus 30 there and 0 there, right? The gap there is going to be again the same gap between 180 there and this intersection there. In other words, this gap there. So that gap is also going to be 30, right? But this case there, we want to go 30 over 180, right? When the curve hits 0 here, but then to get to this point there, I need to add 30 to go along because that's the gap, right? So then the next solution is going to be 180, positive 180, add 30 to get 210, right? And so therefore then, we have the solutions, we have all three of the solutions then. So either x is minus 30, which is what we got, x is minus 150, or x is 210, right? And so that's a really key skill that we hopefully try to pick up, because it's key skill of using the graph to spot all like possible solutions in this way. Will be paramount in the next chapter. So we'll do a lot of practice with this, sure, but I'm going to try and start to pick up the idea of how we can use symmetry and matching parts of the graph to spot other solutions, right? It can be quite a tricky skill, but hopefully with some examples, especially later on, we might start to pick it up. But okay, so that's the solution. That's all the solutions then by using sort of graph, right? But yeah. Right, let's have a look at some an example then. Just one more. It's not a lot to this chapter, but anyway. So I want to practice this skill even more. So this whole idea of using the graph to spot more solutions. So we are told in this case, part A, cos of 30 is root 3 over 2. Use your graph in question 1 to find another value of theta for which cos theta is minus root 3 over 2. So, by the way, when it mentions the graph in question 1, 2, and 3, I've just copied it there, right? So that's the graphs we're working with, okay? So let's deal with part A then. So cos of 30, which I've enlarged here, root 3 over 2. So 30 is one solution there, right? We've got the other solutions to cos x, root 3 over 2. So what values of x can we plug in there to essentially get root 3 over 2? Obviously we know 30 is one solution right off the bat, we're told that. So if we mark 30 then on this graph, it's going to be about there, right? And so we draw it there. Right, so that's when the graph crosses at 30. So then if we draw like a straight line in this manner, both left and right, because obviously that again reflects the line y is root 3 over 2. Right, and so we're essentially saying what values of x crosses this line, which means cos x is root 3 over 2. Anyway, so hopefully you can spot them. We've got one more intersection there, right? So if we read off like that then, the other part of the graph where it crosses this line is over there, which I've circled. So there'll be two intersections, which I've circled. Obviously we know that one is 30, but what about this one? The one on the left that I've circled. Alright, okay. So there we are. So where would that be? Again, we need to pay attention to the symmetry of the graph. So again, hopefully you notice, again, it is symmetrical in the middle at 0. Right at the top of the hump, it's 0. So the y-axis there, which I've drawn badly. There, right? So at the top of the the curve, it's symmetrical on the left of it and the right side of it, right? What that means is that if you were to read off, it's the same gap then between 30 and 0, which would be 30, and this other solution there, right? Try and draw it a bit clearer. Let me draw it a bit clearer. Hang on. 30 there, and so then the gap between 0 and this first solution is 30, but then the gap has to be the same between 0 and this next solution there. So we have to go 30 along because the gap at either end of the curve is 30, symmetrical in the middle of the curve. So if we're going, we have to go 30 to the right here, right? We go to the right by 30. Well, to get to this solution, then we need to go to the left by 30. But then we need to do x about 0 minus 30, which is minus 30. So the other solution, indeed, x is minus 30, and that's the only other one, right? So again, we could sort of use the symmetry of the graph to spot additional solutions, right? So I guess if I redo it one more time, so again, 30 was here. The next solution was there. The gap between 0 and 30 and the first solution, there is 30. Because of the symmetry in the middle again of the curve, or the hump, it'd be the same gap for the second solution there and to 0, which would be 30. But if we're going to the left by 30 from 0, it will indeed be minus 30 down there. Hence it yields the other solution minus 30. Okay, so then part B of this then says that tan 60 is now root 3. Use your graph in question 2, so with this graph provided, to find the other values of theta for which firstly tan theta is root 3 and then minus root 3. So the graph of enlarged is down here. So firstly we need to find tan theta is root 3, but we've already provided that theta is 60 is a solution, right? We were told that in the question. Again, because they told me that tan 60 is indeed this. So we've got one solution already. So again then we need to do the same idea of reading off the graph at that point. So 60 will be about there. Yeah. So then we need to read off the graph then, meaning I need to like sort of extend this line backwards and forwards, and then it crosses over here then, right? So that'd be my next point. There. Okay. So then how do I find that point then, this point here? What value of x, of theta here, is the other solution? So again, we're going to sort of consider the property of the graph. So, well, hopefully you recognise that this has to be 180 away from the first solution 60. So the gap here between this solution and here is 180 degrees. Purely because the graph repeats itself 180 degrees, right? Because of that's the period, right, when the graph repeats itself. And you can kind of see that here because 0 is when it starts, well, it starts at 0, but then minus 180 is when it starts there again. So that means the gap here is minus 180, is 180, sorry, between when it starts at 0. So then if we then read off the graph then, well then this point and then this point have to surely be 180 apart as well, by that logic, okay? So therefore the other solution is 180 less than this, right? Because we're going backwards by 180 to get the other solution. you take away 180, you get me minus 120 degrees. Okay, so then that tells me this value is minus 120. There, okay, cool. Right. So then it says to solve for the next part, tan theta is minus root 3. So the angles or the values of theta, which gives me minus root 3. So 60 again is for positive root 3. They told me that tan 60 is root 3. Remember in the question? So this tells me at 60 here is when it's root 3. But then minus root 3 be negative, the negative version of it in down here, right? So again then, I need to sort of read off the graph there, right? So then when does the graph cross minus root 3? So actually then it'd be that point and that point there, right? There, somewhere there, right? So then if we go upwards in this way, what values of theta right, on the axis? What angle is that then? What for these 2 points? What are the angles here? So we need to again consider the property of the graph. So at 60, it's positive root 3 there. But then what about minus root 3, right? What about again when the graph crosses in this way, right? At these 2 points there. Right. Well, let's start with again this point there. So hopefully you recognise that sort of if I circle this, right, this point of circled is 60. Again, if you read off, but then this point, then they're kind of like flatted in a way. That they're sort of the same, but they're sort of like opposite each other. If that makes any sense. So that means then the gap here is 60. So then again, the gap here will then be another 60 as well. The gap from 60 to 0 is 60. So then to go from 0, so if I highlight that again, so then the gap from 0 to this solution here I circled, there is another 60, right? It's sort of symmetric as well in a weird way. When along the axis there. So yeah, so between the solution 60 we're given here, it's going to be it's 60 away from 0, right? So but then notice it's going to be the same distance away from 0 on the other end to this solution there. So that means then the other solution is going to be taking away 60. So 0 take away 60, be minus 60 there, okay? So that means then that 60 would be there. So then minus 60 would then give us minus root 3 there, okay? And hopefully, again, just once more, see that's because the fact that the gap here between 0 and positive 60 is 60, and it's the same gap between this solution here at negative 60 and 0, alright? But we're going the other way, so it'd be minus 60. Right, okay. So now we've got that out of the way, but then we've got this other solution as well, remember, right? Down here. But then, well, once we found this solution then at minus 60 there, and then we can work out the other solution there, because that's then just going to be 108, another 180. Hopefully you can spot the graph sort of repeat itself, 180 from this point there, because we have an asymptote at 90, minus 90, then an asymptote at positive 90. That's 180 degrees away from each other. And so to get from this point, it's going to be 180 overall there, right? Because it repeats every 180. So it's going to be minus 60 and minus 60 add another 180. So that'll get me positive 120, okay? The two solutions with tan theta is minus root 3 is minus 60 and 120. Okay, so that tells me 120 would be there. Okay. Right. Okay. There we are then. Okay. So the last point, part C, we are told sine of 45 is 1 over root 2. Use the graph provided to find the other values of theta again for when sine theta is indeed 1 over root 2 and minus 1 over root 2. So again, I've got the graph down here. So firstly, I need sine theta is 1 over root 2. I already know that theta is 45 is a solution, I believe. Yes. 45 degrees is already provided to be a solution here. So 45 degrees, if we mark it on our graph, will be there. So then if we read off the graph, the other solution, when it crosses this line, is going to be there, right? So then where would that, if we read off then the graph, where would that solution be? Well, again, the hump is symmetrical, right? It's a hump here between 0 and 180. That means then the gap between the endpoint at 0 and this first solution 45, which is 45, is the same gap between the other end at 180 and this other solution here. It would still be 45, right? Because it's symmetrical, right? Well then, to get this other solution then, I want to take away 45 and 180, right? Because that gap there is 45, right? Same as there. So then to get the other solution, it's going to be 180 take away this. And that should be very, very, very reminiscent of when we did the ambiguous case. That's exactly what we did with that as well. We took 180 from the angle. So that we get 135 degrees, right? So that solution is 135 degrees there. So there we are then. Then part 2 then, it says the angles with sine theta is minus 1 over root 2. Right, so let me get rid of this then. So obviously again 45 is positive 1 over root 2. But then we want the negative, right? So it's going to be down there somewhere. Well then, if we read off the graph then, right, there, right, if we extend that line, that line cuts the graph at these 2 points here. So these are the 2 solutions we're interested in. What angles then, there and there, get us, right, that sort of solution. Okay, so again, it's the same sort of idea when we looked at in the previous example. The idea that, firstly, if we just consider this solution here, well, this 45 degree here, that solution in here, well, again, the gaps are going to be sort of the same between the end at 0 and 45 there, and then the gap here between 0 and this other solution there, right? So then, obviously, we're going to take away 45 from 0, because to get positive 45, we added 45 to 0, right? Because that was the gap 45. To get to that solution there. But now I want this solution there. I instead need to take away 45. So that's what I'm going to do. So then theta is going to be 0 take away 45, which is just 45. Minus 45, sorry. But that's the one solution then. Okay. So this is then going to be minus 45. Try not to map my graph too cluttered. I really do apologise if it's a bit messy. So 45 was there. So we've got minus 45, but then we need to read off the graph then. But then the other point will be there somewhere. Well, again, how are then we going to get that other solution here, right? But again, it's the same sort of idea then. The gap at either end of the curve, this gap is 45, right? To get from 0 to minus 45. That's one end of the curve. But then this other end, at minus 180, to this solution is also going to be 45 then, because the ends are symmetrical again, because the curve is symmetrical. With that in mind then, well then we need to get minus 180 at the end, and then we need to add 45 to it to get to that other solution. So it's going to be minus 180 add 45. That will get me minus 135 degrees. Right, so then that would be that solution here, minus 135. Because again the gap is 45 there between the end of the curve and that point here. Likewise between the other solution there and 0 would also be 45 there. The gaps have to be the same. Okay, and also we got minus 45 because positive 45 would be there. So again the gap between 0 and 45 there has to be the same between that gap as well. Okay. Anyway, so that's the core idea then. So that's all the solutions then. So that's really sort of the gist, right, of using the trig graphs to spot solutions, right? We will be doing a lot more of this in the next chapter. So we really will build upon and practice a lot of this, right? The idea of solving equations by considering the trig graph, which is why learning the basics and learning what the graph looks like is very important. Even if you have a graphical calculator, I think it's so important to just be able to quickly remember and spot and know what the trig graphs look like and what sort of how it takes place and what the values sort of are, because it makes it working and it makes you how you think a lot quicker. But anyway, so that's just the trig graphs. We will look a bit more complicated trig graphs by transforming them. So doing stretches and stuff like that in the next video, at the end of the last part of this chapter. But yeah, that's just using the trig graphs, right? Remember, that's the trig graphs and how we can use them to get the solutions, right? So hopefully it made some sort of sense. But yeah, so that's it for now. So I'll see you next time.